Now we're going to get to bonding and antibonding. You guys taken general chemistry?
Yes, I have.
Not you, Chris? In chemistry? Not since high school. Like me in biology. Did you talk about bonding and antibonding orbitals and wonder why?
Yeah, why they bond, you mean?
Well, why you have some bond and some don't? Why do antibonding orbitals exist? That's what we're going to learn about today. So this we've already seen. For indistinguishable particles, you have to have a superposition state, which brings in this plus or minus. You're adding one combination, that is state A has for particle 1 and state B for particle 2. And then the mirror of that, state B for particle 1, state A for particle 2. Because you can't tell the difference of particle 1 and particle 2. All you know is one's in A and one's in B. And so you had two ways of putting that together. If you put the plus sign, then it was a boson. That's just the definition. And if you put the minus sign, now the plus is symmetrical. Well, we'll see the symmetrical and the anti-symmetrical in just a second. The fermions is when you put in the minus sign. And then we looked at this with the fermions. If you were in state, if state A was the same as state B, then this would be particle 1 in state A, particle 2 in state A, particle 1 in state A, particle 2 in state A. It would subtract out to 0. That is why fermions have the Pauli exclusion principle. They cannot all be in, or they cannot have two in the same state, or you get 0 for the wave function. With the bosons, because of the plus sign, you just made it bigger. There's no big deal. So bosons have no such restriction. In chemistry, you just tend to feel that that's a rule for quantum physics, that no two particles can have the same quantum number. In quantum physics, you learn it's not no two particles can have the same quantum numbers. It's no two indistinguishable particles that are fermions. You have those two have to be indistinguishable. If you can tell the difference, if you have the blue ball and the red ball, then you could have a wave function with the blue balls in the same state as the red ball. Now we get to something new, right? So 2 minutes of quick review from last class period. Now something new. The exchange operator. The exchange operator is an operator we introduce for the case of two particles, and we say, what difference does it make if we switch the particles? So if I switch particle 1 with particle 2. And so the exchange operator, notice there's something unique about this. It looks like it's the same wave function until you look at it carefully. Particle 1, particle 2, compared to particle 2, particle 1. So the exchange operator is changing which particles in state A and which ones in state B. And the eigenvalues for the exchange operator are that you're going to stay in the same state. Well, you have an eigenvalue of 1 when you exchange them. Now, I said you're going to have an eigenvalue of 1. It's the eigenvalue of the exchange operator squared that's 1. It could be plus or minus 1, because if you exchange them, let me just go through that to make sure you understand. This equation here shows one of the two possible outcomes. So I really should have written it this way, and I'll show you why. You have the exchange operator let's just do this here. So the exchange operator is operating on that combination. What it's going to produce is that, right? Switched the particle subscript 1 is now in state B instead of state A, and particle subscript 2 is now in state A instead of state B. So if I were to put that on my psi singlet state, so there I've written out the singlet state. I'll change the color for the singlet state just to make it clear that this is the singlet state. That's not enough of a change in color. That's the color I was looking for. Okay, so I have the exchange operator acting on the singlet state. That's going to give us an easy enough 1 over square root of 2, doing all of those switches, psi B, R1, psi A, R2, minus psi A, R1. So there I've done the exchange operator, what it does. But if you look at this, actually, now that I think about it, this here wasn't incorrect. It just wasn't showing the eigenvalues. Yeah, it wasn't incorrect because it had the 2 switch. It wasn't the same state. So now that I've done this, I can look at this and say, wait a minute, I could just reorder this minus 1 over square root of 2. And I'm going to put this one first. I factored out the minus sign, so it's going to be positive. This one here is now going to be negative because I factored out a minus 1. But what is this whole thing? That whole thing is minus psi for the singlet. I said singlet. I shouldn't have. Well, yeah, it is the singlet, actually. That's psi 0, 0. That's a better way of writing it. The singlet state is 0 for the capital S. Or the lowercase s quantum number. Yeah, for the lowercase quantum number s. So that's the exchange operator acting on psi 0, 0. If I did the exchange operator acting on psi 1, 0, psi 1, 0 is the symmetric one. And so that's everything the same except for the plus sign, right? Well, in this case, there's no minus sign to factor out. I just changed the order. And this here is, well, when I do it, I'm not going to do the rest of the math because I'm pretty sure you can see the rest of the math. This is equal to psi 1, 0. So the eigenvalue here was 1. Here it was minus 1. And so that's where the statement I have here is clearly the eigenvalue of the exchange operator squared is 1, so the exchange operator must have eigenvalues of plus or minus 1. That statement was made from if I did that would have to exchange R1 and R2 and then exchange them back. And so it would have to be so that's the eigenvalue squared is going to have to be 1. So this statement was a correct statement. This here is the easy mathematical showing, yep, of course it is. So the Hamiltonian is going to be symmetric under exchange. That is, if you change particle 1 and particle 2, we have the Hamiltonian only in terms of the R, the separation between the two, and the position of the center mass. So the Hamiltonian doesn't care where the positions are. So the Hamiltonian is going to have to commute with the exchange operator because the Hamiltonian doesn't care where the positions are. So now if we look at if we look at them, we see that bosons are symmetric under exchange while fermions are anti-symmetric. What that means is this was the -1 for the eigenvalue, and this was the +1 for the eigenvalue, symmetric and anti-symmetric. So that, that's pretty straightforward. But this brings up some interesting things. What if we want to calculate, what is x1 minus x2? x1 minus x2 is taking a one-dimensional case and taking the separation between them, or R. So this is really just the expectation value of R squared, the separation between the two. We're going to calculate this in long and gory detail. Actually, if I don't make it long and gory, we're just going to finish class early. It is long and gory calculations. But we're going to calculate the expectation for that it's one dimension. That's why it replaced, with x's. So using psi is x1, x2, just to make sure we understand what the nomenclature is. It's telling the first stage with respect to is for particle 1, the second stage for particle 2. Then if I do the position squared for the first particle, remember, just by definition, come on. I have that where psi is a function of both x1 and x2. And then using our definition here for what psi is, this can be further expanded into so there's psi star, then my operator, and then psi, and then I have, of course, dx1, dx2. We have to integrate over all space, which is all space for particle 1 and all space for particle 2. So that's why it's a double integral. But x1 is unrelated to x2, and so I can separate these into two integrals. First, I'll put the x1 material and then I will put the x2 material, because x1 and x2 don't interact. There's no relation between them. Well, which one of these can you do easily?
The better one is just one.
Right. You had a question?
Why is the operator not x squared?
Because I made a mistake. That is a mistake I made from the first writing and did not correct it anywhere because I'd made it. Thank you for the correction. Yeah, that would have been a really good question. It seemed to me that it was always. Okay, So the second integral is easy. The first one, I will just put what it is. That's the expectation value of x1 squared. Right, that's by definition, that's the expectation value of x1 squared.
Right.
Life came out easy there. And notice it has here, if it's in state A, because these were state A. Right, because the expectation value does depend on your state. And these were both psi sub A. Yeah. How did we have something different than what we started with? Hey, look, you proved 1 equals 1. You get a gold star for the day. All right. So then you do the same thing for particle 2, and particle 2 is going to be, oh yeah, it dropped off the 1 there and just said the expectation value for state A. Because, of course, you don't have an x1 anymore when you integrate x1 out. Doing it for particle 2, it's just going to be the expectation value of x squared for state B. Now, the interesting part comes when you're doing x1, x2, because the expansion here of expectation value of this difference squared of the r, when you do this squared, of course, an intermediate step was not shown. When you, do you guys use the term FOIL it out? Because I never learned that until I was a teacher.
I mean, yeah, fine. Or whatever else.
Right, so if you square it, you have that for the square, and then, you know, when you do an integral of a plus b plus c, you can do the integral of a plus the integral of b plus the integral of c. And so that's how it got to this set. So we've just done this, and now we have the last one to go. So x1, x2 is the last one. So doing x1, x2, notice there's no square here. And this looks really interesting, so I'm going to go ahead and actually, it's correct. It's correct. It just looks funny to me at my first glance. If we do the work here, we're going to have x1, x2 instead of x1 squared or x2 squared. And so if we do the work, we're going to have just a single x1 here and a single x2. Okay, you can't see where I'm doing this, can you? I bet you there's a pointer that I've never used. That's not it, apparently. Pointer. Okay, forget the pointer tool then. Let's go with this. Yeah, that's not what I want either. Forget them. The first one is supposed to be a pointer, but it wasn't working. Nope, that does the same thing. Interesting. Let's not worry about that. I had figured this out before. There was a way to do it. Okay, well, this here, you see, do you see the little squiggly that I'm making? That there would just be x1, and then you're going to have an x2 right there.
Right.
And so it's pretty clear to see that you're just going to get expectation value of x for state A and expectation value of x for state B.
And the difference between x1, x2, and x is x1 is the position of the first particle from the origin, and x2 is the position of the second particle from the origin.
That's right.
X is the difference between.
And yeah, well, no, x is not the difference between in this calculation. Okay, so from what we've done before with R, that was exactly the definitions. In this definition here, it's just saying the position in X space if you're in particle A. So it's a different meaning than the separation between them. Do you understand what I said, Indy?
I'm just trying to think, like, if we were to try to use this, because, like, if say I was asked to do the expectation value of X in the state A,
Okay, we're doing one dimensional, but I drew my graph in 2 dimensions. So we're looking at each particle. So let's say, just for grins, here's particle 1 and here's particle 2. We're measuring x1 is going to be that, and x2 is that, right? We're just measuring from the origin to x1 or x2.
Okay.
And then when I have the expectation value of x, if the expectation value was here, then this here would be my expectation value for x. And we used an A or a B to say in state A, where's the likely position? In state B, where's the likely position? But in all of these cases, we're talking about the position of a particle with respect to the origin.
Okay. Okay, I understand. I wasn't thinking about the definition of the expectation value, but I was saying that. So, okay.
Well,
That makes sense now.
it's a very good question. It's one that I could see myself making. So we've done these 3 expectation values, so we can put them into our equation for the expectation value for the separated particles, and we get this result. Easy enough. This was for distinguishable particles. This was not for bosons or fermions, because your combined state for bosons and fermions is a superposition rather than just a product of the two. So now we found what the separation, the expectation value for separation squared is. Separation squared, so we don't have to worry, is it going to, is 1 to the left of 2 or is 2 to the left of 1, right? We just have the separation squared. Now we do it for bosons. So for bosons, we have the superposition state of A is in state, or particle 1 is in state A and particle 2 is in state A with the plus sign. So we do the whole thing again. So we do the expectation value of x1 for this state. And of course, it's more complicated. Of course. Because why wouldn't it be? So let's write this one out. And of course, I'm only going to do one example again. No, x1 squared plus that's a bigger integral. And it's more complicated. If we multiply these through, I'm going to have that and that. Well, let's bring out the 1/2 first. So that's the term I get with the two underlined ones. And then dx2, not dt2. Now this one here is going to be simple because it's just like what we've done. But then I've got to go to the next set. So if I do that one, what are you going to get? Okay, for the top one, this here is just, well, this here integrated over x2 is normalization, right? And this here integrated over x1 is going to give me that. Now in the second one, what am I going to get for this integral?
Since they're in different states, should it be 0?
That's correct. That's the whole thing I wanted you to see. They're in different states, so we have orthonormal. The orthogonality means that one's 0. Yay! So now we go to this one. This one combined with this is going to be another term, another one that gives us 0, right? Because it's going to have the A star in x2 and then B in x2. That's going to give us 0. So plus 1/2 blah blah, that gives us 0. Plus 1/2 the last one. The last one's going to be combining magenta, this with this. Look, I have 2 lines under each of them because, well, that's how it works out, I mean, obviously. And so that one is going to have the B's in x1, and hence the expectation value of x squared for state B.
Right.
So we can see the gory math. And yeah, it is more math, right? It's not at any stage hard as long as you understand your quantum physics rules. Well, the Hilbert space rules is what they really are. And so we see that's what we get for the x1 expectation value, x1 squared expectation value. And if we did x2 expectation value, x2 squared expectation value, we know we'd get the same thing, right? Because of the symmetry, it'd be the same thing. And then we have to do x1, x2. Do we really want to do x1, x2? I suppose we do. So if we do x1, x2, we're going to have, when we do this, instead of having x1 squared here and nothing there, it's going to be an x1 here. So I'm going to be an evil person and shift this. Well, if I do this, what's this integral right here? Yeah. The 1/2's out front, but right now I'm focusing on that. And this part, the second part, so this one here is going to be 1/2 expectation value of x in A expectation value of x in state B.
Right.
And the bottom one, the last one, is just going to be reversed. So this one here is likewise going to become that, because the symmetry. Then we have the two middle ones. What's that? Well, look at my solution. It's of course this. That's just rewriting it. We have two of them. Each one has an a and a b in the same x, so I just dropped out the subscripts and said we have two of these. 2 times a half is 1. And so I just put that integral.
Now, out of curiosity,
Yeah.
Why in this case did we combine it and write it as that? Is it because of the x in both integrals?
So you're saying, why is this not x1, 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 x1? Is that what you're asking?
Well, no, it's why did they not go to 0?
Oh, yeah, they didn't go to 0 because the yeah.
Because the x in both integrals?
Because the function is no longer psi mod or psi a psi b. It's psi a psi b times something. So times a variable. If it was a constant, it would go to 0. You're right. Think about sine cosine. Or no, let's go to sine of n pi over lx times sine. So if it's sine of pi over lx times sine of 2 pi over lx. Those are different orthogonal states. The integral is going to have to be 0 if we're in a well. But if I did x times that, it's a different function. It's a function that now is going to have a linear aspect multiplied by the other one. And so what before was symmetric is now having that symmetry broken, so it's not going to come to 0 anymore. Okay. So it's because we have the additional variable x multiplied by it that it's not 0.
Okay.
So it's a little more interesting. We don't have a way to evaluate that unless we have a function. That's why it's just written as the integral. Why does it have the mod squared? Because the order is reversed between which one is starred, right? This is A star A star A and B star B with the 1. And when we do it the second time, it's, well, actually, when I look at these, it looks identical. Now I'm thinking about this. If I do this with this, I have A.
I think you're looking at the wrong one.
Yeah,
Look at the light blue one.
yeah, that's the problem. Yes. But look at it again. Yes. This is A star with B, and this is B star with A. So they're the same integral except for it's a complex conjugate. And so that's why it's the mod squared.
Okay.
Yeah. I would have had a hard time explaining that. I was like, they. All right. So now plugging the x1 squared expectation value and the x1, x2 expectation value in by analogy, the x2 squared expectation value. We can put it in and we have the expectation value of the separation squared is the expectation value, the separation squared for indistinguishable, minus this term. Now, when you do a mod squared, it's always a positive value. And so that means that they're closer together. When you are in the boson, when you have two bosons, the separation is going to be closer than it would be if they were two indistinguishable particles. Kind of a surprising outcome. Don't you think?
You mean that if they were distinguishable particles?
If they're distinguishable, they would be farther apart than if they're indistinguishable bosons.
Right.
And that's just a result of what the quantum physics says. It's not, hey, we did some experimentation and found this or something. It's what the quantum physics says. It's a prediction then that, of course, has been tested and verified. Now, what if they're fermions? What's going to be different if we change from bosons to fermions?
There's going to be some negatives thrown in there.
It's going to put a negative right there to start with. And so that negative is going to translate to this being minus for those two.
Right.
Now I'm going to put the pluses back. I'm not going to do any more messing around with that work. So if I do the fermions, everything looks just about the same. The x1 squared expectation value is the same as it was before because it has the plus sign. And of course, the x2 squared expectation value will likewise be the same. But the x1, x2 is going to have minus for those two middle terms. And so if I do my expectation value for the separation squared now, this here again is the indistinguishable result. But now it's farther apart. Now, how's this going to play out? This says that you're going to have something if it's two fermions, they're farther apart. If it's two bosons, they're closer together. And if they're indistinguishable, it's somewhere in between. What meaning is that? How is that useful? We call this the exchange force. There's some kind of force associated with the quantum mechanics that says that you can't have two fermions sharing the same space with the same quantum state. And so that's where we have the term, I actually clearly hit the wrong button, my brain missed. The summary of the exchange forces is that you are going to have the bosons closer, the fermions farther. This makes a real big difference in cosmology. We have stars, and when the stars die, if they're a big mass but not big enough to become a black hole, what do they become? You may not know this. You may not be into astronomy. Okay, stars collapse. Of course, I didn't even spell collapse right. Low mass stars become white dwarfs. And then middle mass become what you said, neutron stars. And what do the largest ones become? I say largest. Somebody is going to listen to this and say, if it's too large, it loses mass so rapidly in its death stages that its mass is too low to become. That's true, but then it's not that large at the very last moment, okay?
Yeah.
So what do the large ones become?
You said the biggest ones become black holes, right? If they have too much mass.
Well, that's where I said some purist is going to say, no, the biggest ones, if they're too big, they lose mass so rapidly they won't become a black hole because they're not going to be that massive at the end state. So the biggest ones actually don't become black holes is my understanding. But the really big ones become black holes. Your basic rules are if it's more than about if it's more than 3 or 4 solar masses, it'll become a black hole. Neutron stars are between I'm just going to put 4 here. SM is solar masses. So if it's bigger than 4 times the mass of the sun, it'll be a black hole. If it's bigger than 1.4 times the mass of the sun, it'll become a neutron star. This is not astronomy class. That's enough on that. Why am I talking about this? What's going on in stars right now? Our sun. What's going on in our sun right now?
Fusion.
Where hydrogen is built into helium at temperatures of millions of degrees. Yeah, it's really hot, but not billions hot. So hydrogen fuses into helium. Right now, you have explosions, a fusion bomb occurring continuously. So that'd be a fusion power plant if it's continuously. It's just it would not work on Earth. And so you have all of the energy being released that's trying to make the sun explode. But gravity's holding it in, and so you have a stable balance between the explosion outward and gravity pulling it. But as this progresses, the amount of fuel is diminishing. And so eventually it's going to run out of enough hydrogen and the fusion's going to stop. You have gravity pulling in, nothing pushing out. What's the obvious result? It becomes a lot smaller and a lot more dense. What's going to stop it from shrinking?
The atomic forces.
It's actually what we just talked about. It's going to stop shrinking because you're going to have electron degeneracy. The electrons, being fermions, are not allowing it to get too close. And so you have what we call an electron gas that's keeping it from collapsing. So this white dwarf, which is going to be, we say that it's a diamond, that it's primarily carbon atoms, carbon and oxygen, some helium, in the white dwarfs. But it's not the carbon, oxygen, and helium that's keeping it at its size. It's the electron degeneracy. It's this exchange force. Did I call it exchange force here? Yeah, I did. It's this exchange force that's keeping it from collapsing. And if you put in more mass, the force of gravity becomes bigger, and it will very slowly shrink as you put in more mass until you get to 1.4 solar masses. That's the calculated level where you can overcome this exchange force and force things together. And so what happens if you have a white dwarf, like our sun will become a white dwarf because it's clearly less than 1.4 solar masses. If it was with a companion star that is dying, that companion star dying would be blowing off copious amounts of mass, and the white dwarf next to it says, hey, I'm a little ball of mass, I could take more. And so it accumulates mass if you have a binary system with one star and a white dwarf and the other one dying. And if the white dwarf gains mass, primarily helium, periodically you'll have the helium on the surface reach a high enough temperature and pressure to undergo fusion, and it kind of burps, has a burst of energy. It's called a nova. And then it just has more helium to add to the mix until you get up to a total mass of 1.4 solar masses. At that point, the electron degeneracy fails and everything is forced together. And when you reach this point, kablooey, you have a supernova. So a supernova occurs if you have a white dwarf that reaches a high enough mass to overcome this exchange force, this force associated with electron degeneracy. Neutron stars, during the death stage, you had enough mass, you're over 1.4 solar masses, that it crunched right through that, and it forced all electrons into the nuclei and broke apart all the nuclei, producing a whole bunch of neutrons. So you have a lot of particle physics interactions that created just a whole bunch of neutrons. So all the protons, all the electrons have undergone particle, right? A proton and an electron does not make a neutron. It's much more complicated than that. But they have gone through a process that's converted everything essentially into neutrons. So neutron star is neutrons all crushed together. What keeps them from squeezing down smaller and smaller and smaller? It's the degeneracy of neutrons. Once again, neutrons are fermions. They're half-integer spin particles. You can't have two indistinguishable neutrons in the same state. And so the neutron stars are once again held up by neutron degeneracy, by this that we've learned. But if you get up to about 4, and this number, like I said, they say from 3 to 4 solar masses, it's not a perfectly known number. Then you will overcome the neutron degeneracy, which gives you. Now, I learned to call this a supernova. I think sometimes it's called a hypernova. It's a different kind of supernova, but it's a supernova. You have a type 1A, type 2. You have different types of supernova. This is just a different type of supernova.
So what exactly is a supernova? Is it just a big explosion in space, or like exactly what comes after the supernova?
Okay, and actually I was wrong. Hypernova is when you create a black hole. It's not. So these are both supernova. The hypernova is when this occurs. It becomes. The star underwent a hypernova and became a black hole. So what happens after? Yeah, we only have 4 minutes left, so I won't go on to the lecture. I'll just answer this. So, white dwarf undergoing a supernova, it creates a cloud. What do we call a cloud in the sky? We call it a nebula. So you have no chunk anymore. You just have a huge amount of energy that erupts and a cloud of gas. And of course, a lot of mass is converted to energy in the eruption. And of course, the gas is now moving away, which is why it's not a chunk. So the white dwarf becomes just a nebula when it undergoes supernova. The neutron star, when it undergoes a supernova, it's going to create, trying to think about this. A black hole. Because you have so much mass that it now is just collapsed in on itself.
Right. So it technically does have a hypernova rather than a supernova.
Yeah, I actually did. Maybe it doesn't create a black hole. I'm thinking about this, trying to get straight. I didn't prepare this, for this class. It's astronomy. I'm going to have to look back at it and make sure I have that straight. Yeah, I mean, a neutron star is not going to create a white dwarf remnant. And yeah, a white dwarf can't create a supernova or a neutron star. So yeah, I think that's where it goes, but I'm going to have to check.
Okay.
All right. Okay, we're finishing a minute early. Go ahead.
One quick question on the homework.
Yeah.
So with the problem number 4, the last one, we're supposed to use the ladder operators for calculating Lx and Ly.
I was trying to do some calculus. My son's in Calc 1, and of course, I didn't think about doing this the easy way. It's so embarrassing. He's in Calc 1. I should be able to do that stuff in my sleep, just in case you're wondering about that. Here.
So for this problem, are we just taking L comma M1, L comma M2, and then when we calculate the values, that's when we get the LX and the LY? Is that what we're essentially doing?
What you're doing, I had it here, of course, before and then erased it. You know that L plus is equal to LX plus ILY. L minus is equal to LX minus ILY. Therefore, L plus L minus is equal to 2LX, and L plus minus L minus is equal to 2ILY. Therefore, it's not expectation value. I'm going to erase the commas because it looks like I was putting L1.
Yeah, that's what I ended up doing. That's valid.
Right?
Okay.
So I just took this here. I divided by 2, obviously. I figured you could do that. And then you just evaluate what these give you.
Yeah. Okay.
All right?
Yeah, I wasn't sure if you were, when you said use ladder operators, if you were calculating an L plus L minus, well, L minus, but I didn't realize we were taking L plus L minus and L plus minus L minus.
Yeah. We're just using the ladder operators to give us an easy way to do the evaluation.
Yeah.
There's hard ways of doing it too.
Yeah. All right. Sounds good.
All right. Go ahead.
I actually have one more question.
Sure.
About, not about homework or anything, but about the neutron exchange forces.
Uh-huh.
Why is it that, are the neutron exchange forces stronger than the proton-electron exchange forces? Is that why the neutrons break down after the...
I don't know. I don't have an answer there.
Okay.
Yeah, I know. That's really the unfulfilling answer, but that's what I got.
That's all good.
All right. I'll see you guys.
All right, thank you.
Yeah.